Okay, so today we're looking at chapter 6, and this, section 2.6. This has to do with problem solving and dimensional analysis. Dimensional analysis is probably the most important technique that you can use that's going to help you do chemistry problems. I learned this as a junior in high school in physics, and it's probably the most valuable thing I learned in all of high school was dimensional analysis. So to understand this, we have to review math just a little bit. We need to remember that anything divided by itself is 1. We need to remember that multiplying anything by 1 doesn't change it. Okay, so if we have 6 divided by 6, that equals 1. The same thing works with units. Centimeters divided by centimeters equals 1. So if we take the number 17 and multiply it by 6 over 6, we recognize that 6 divided by 6 is 1, and so this is just 17. It hasn't changed it at all. If we take the number 23 and multiply by centimeter over centimeter, that equals 1. Multiplying by 1 does not change the number. And these are the core ideas behind dimensional analysis. So we can think of a problem such as this. You bought 5 dozen eggs at Costco. How many eggs did you buy? 60. How did you do that? You took 5 times 12. Okay? So you actually know how to do this whole unit conversion process with units that you're familiar with. Okay? I'm going to show you the mechanics of this so that you can do the same thing with units that you are not familiar with, because we're going to run into those in chemistry. So we have something called equivalence statements. These are just equalities. These relate 2 different quantities, like 1 dozen eggs equals 12 eggs. These are just 2 different names for the same thing. My 3rd son is named Thomas. We never call him Thomas. We don't even call him Thomas when he gets in trouble. It just seemed like Tommy would be a ridiculous name for an adult man, if he became president. President Tommy Kawagoa. It's kind of not right. So we named him Thomas. Thomas is his given name, but Tommy is his nickname. Tommy or Thomas, we're referring to the same person. So whether you call it 1 dozen eggs or 12 eggs, you're referring to the same amount of eggs. A foot equals 12 inches. It's the same length. You can call it a foot, you can call it 12 inches, it's exactly the same. A gallon equals 4 quarts. These are equivalence statements. From these equivalence statements, we can make conversion factors. A conversion factor is just, we take that equivalence statement and make it into a ratio. The two different parts. And these conversion factors are mathematically equal to 1. So from each equivalence statement, we can make 2 different conversion factors. So from 1 dozen eggs equals 12 eggs. We can make 2 of them. So I'm just going to draw here. So if we take 1 dozen equals 12 eggs. The way we get these conversion factors is, here we have an equality. If we do the same thing to both sides, it's still an equality. Like if you have a teeter-totter that's balanced and you put a 5-pound box on this side and a 5-pound box on the other side, it's still balanced because you did the same thing to both sides. So I'm going to take this side and divide by 1 dozen, and I'm going to take this side and divide by 1 dozen. So here, I have that conversion factor. If I took the equality and instead divided by 12 eggs on both sides, I would end up with the other conversion factor. What's important is that what's on the top equals what's on the bottom. 12 eggs is the same as 1 dozen eggs. And so this is equal to 1. And when we look over here, 1 dozen over 1 dozen equals what? 1. So these conversion factors are mathematically equal to 1. Whoops. We can do it with other things too. A foot equals 12 inches. So we have 1 foot per 12 inches or 12 inches per 1 foot. We can do it with the gallons and the quarts. A gallon equals 4 quarts. So 1 gallon divided by 4 quarts, those two things are equal. This is numerically equal to 1. And so if we multiply something by that, we're not changing the value at all. So to do dimensional analysis, we multiply by the conversion factor that gives us the units that we want. So we're doing this, it's driven by the units. What units do we want to get? What units do we have? And that's going to tell us what to do. So 5 dozen eggs, and we're trying to get the number of eggs. We did this problem in our head, but I'm going to show you how we do it all written out. So this is what's called a path. It tells us we're going to start with 5 dozen eggs, and we want to end up with number of eggs. We need to know the relationship between these. So we know that 1 dozen equals 12 eggs. That's our relationship. Then we take that path and we start over here with the number that we were given, 5 dozen. And for every arrow, this one just has 1 arrow. For every arrow, we're going to have a conversion factor. The units on the top of this, dozen, and then we need a unit here, those are going to be the same as the units in this path that we wrote out. 5 dozen eggs to number of eggs. So this is just going to be number of eggs. Then we want to get rid of this unit of dozen, and so we're going to divide by it. Because anything divided by itself equals 1, and multiplying by 1 doesn't make any difference. So dozen over dozen, we say those cancel out. They poof, disappear. It's as close to magic as we get. So we look at the units and get those in the right place, and then we fill in the numbers, because a dozen eggs is not the same as 1 egg. And so here we need numbers. This is where we look to our equivalence statement or our conversion factor. We may have written it out as a conversion factor. This is an equivalence statement. So 12 eggs equals 1 dozen. So we need to put the 12 with the eggs and the 1 with the dozen. The most common mistake is people switch the numbers, and they tell me that 1 egg equals 12 dozen eggs. Now with a unit like dozen, we recognize that that's ridiculous. But when we get to grams and moles, and you switch the numbers, it's not necessarily obvious to you that you screwed up big time. So we need to learn how to do this first with things that we do understand. Now we do the math. 5 times 12 is 60. And then we look at the units. The dozens canceled out, and the unit that's left is eggs. And you guys did that in your head when I asked you that question. I bought 5 dozen eggs at Costco. How many eggs do I have? You knew that you needed to multiply by 12. This shows us how to do it when the units don't make sense to us. So we're going to follow the same pattern. Any questions yet? And I think this is all, let's see where this goes. Yeah, that was all written out there. Because this was before I figured out how to use my technology sometimes. It doesn't work all the time. So, steps for dimensional analysis. Some people really like, just give me a set of directions that I can follow. So, we try to accommodate you on that. So, dimensional analysis is changing from one unit to another using conversion factors. The first step is to convert. The first step for converting is to use an equivalence statement that relates the two units. Okay, so like the one we just did, we know the relationship between number of eggs and dozen. You have to know that relationship. So the equivalence statement was 12 eggs equals 1 dozen. Then we're going to choose the appropriate conversion factor. Remember, from each equivalence statement, we could make 2. Then we're just upside down of each other. You choose the one that's going to make the units work out the right way. Then you multiply the quantity that you're starting with by that conversion factor to give the quantity with the desired units. Important at the end, check that you have the correct number of significant figures. And also ask yourself, does my answer make sense? Okay, and one way to check that is with what's called a bigger, smaller rule. The bigger number goes with the smaller unit, and the smaller number goes with the bigger unit. And I'll give you examples of that. So let's do some examples here. A golfer putted a golf ball 6.8 feet across a green. Now, we don't know whether it went actually in the hole or not, but he putted it 6.8 feet. How many inches does this represent? So first we have to identify what are we starting with. Well, this problem is fairly straightforward. We only have one number in here, so that must be what we're starting with. We've got 6.8 feet. So that's what we're starting with, and then we need to know, where are we going? What unit is it asking for? It's asking for inches. So that's what we're trying to find. So now we need to figure out, how do we get from feet to inches? This is a little bit like crossing a stream. Sometimes the stream is very narrow and you can just jump straight across. Other times it's wider and you need to find a stepping stone to step on in between because you can't get across in one step. And that happens with these conversion problems too. So do we know a relationship between feet and inches? Yeah, we do. 1 foot is 12 inches. So that tells us we can do this in one step. So we can go directly from feet to inches. The relationship is that 1 foot equals 12 inches. Now, if you did not remember that, you'd have to go look it up. Okay? But this is one that we assume is basic knowledge, just from, growing up and going to school. So now we're going, this is what the book calls the path. That's our path. It's like our road map. It tells us where we're going. It's like if you're going on a trip, first you need to know where you are, then you need to figure out where you're going, and then you need to figure out how you're going to get there. And if it's a somewhat complicated thing and you've never been there before, you might need to write it down, right? Because you're like, I need to take this road and that road and that road, and then you just start driving, and then you're like, oh, wait a minute, what was that highway I needed to turn off on? It helps if you've got something written down. Unfortunately, they haven't invented GPS for word problems yet. Maybe they'll get to that, but not yet. So this is our map, and when we get lost and we forget what we were doing, we go back to the map. It reminds me a little bit of Dora the Explorer. Who do we call when we don't know where to go? Map. And then we look at the map. Well, we're here, and we need to cross the Stony Brook, and then we need to go up the Green Mountain and over the hill, and then we'll get to Sammy the Squirrel or whoever. And then they chant it over and over again. I've watched far too much children's television. I don't usually sit and watch it, but it's on in the background, right? It started with Barney 20 years ago. Yeah, so I've been through all of them. Where was I going? Oh, the path. Yes, the path, right? I also have child-induced attention deficit disorder. Okay, so there's our path. Now we can write out our equation. We start with the number that we were given, 6.8 feet. You have to write the units, okay? You have to write the units in. Otherwise, you're going to get wrong answers, okay? For every arrow, we have one fraction. So here's one arrow, we have one fraction. So we draw the fraction line. There we go. We look at the path and we see what are the units. It goes feet to inches. Okay, feet to inches. So that's going to be the units here on the top in the numerator. So feet, then we need to put inches over here. In the denominator, in the bottom of the fraction, we're going to put this previous unit. We want the feet to go away, so we're going to divide by feet. Feet divided by feet is 1, cancels out, poof, it's gone. But we need numbers in there because 1 inch does not equal 1 foot. So we look at this guy here, and we go back to our conversion factor or our equivalence statement that we wrote down, and we see that 12 inches is 1 foot. So 12 inches is 1 foot. And then look at that and ask yourself, does the top equal the bottom? Does 12 inches equal 1 foot? Yeah, it does. Okay, then I'm good. Now we do the math. And you take your calculator, and you got 6.8 times 12. Helps to start with a clear display. And if you want to, you can divide by 1. It's not going to change anything. And the calculator says 81.6. And what's the unit? Inches. The feet canceled out. So that's what my calculator says. How many significant figures should my answer have? 2. Because the number I started with, 6.8, had 2 significant figures. This equivalence statement is exact because it's within the English system. A foot is exactly 12 inches by definition. So this is limiting our number of significant figures, and so we're going to take 81.6 and keep the 8 and the 1, and the next number that we're dropping is 6, which is 5 or greater, so we round up, and we're going to say this is 82 inches. That's my final answer. So we check the sig figs, and now we check to see, does this answer make sense? Let's do the bigger, smaller rule. Feet and inches, which unit is smaller? Inches is smaller. Inch has a unit, has the number of 82. It has the big number with the small unit. Here we've got the small number, 6.8, with the bigger unit. Because if you make the unit bigger, then you've got fewer of those units. Any questions about this one? Yeah, blah, blah, blah. Okay. So here's another example. An iron sample has a mass of 4.5 pounds, 4.50. What is the mass of this sample in grams? And then in parentheses, they're giving us some information. Some of these problems you'll run into are going to have extra information in them. Some of them won't. Students often have trouble figuring out, especially when there's multiple numbers, well, which is the one I'm starting with? Well, if you've got something in parentheses like this, these guys are conversion factors that you're being given. We're giving you those so you don't have to go look them up, just to make your life a little easier. And so if we look at the problem itself, there's really only one number in there. And so that's the number we're starting with. We're starting with 4.50 pounds. That's kind of a sloppy B. Okay, what are we trying to find? What's the question? What is the mass in grams? We're trying to find grams. I'll move that over. Do we know a relationship between pounds and grams? There is one, but let's assume that this is all the information we have. Anybody know the relationship between pounds and grams off the top of their head? I can't quite remember. I think it's like 454 something, but I'm not real positive about that. But here we have relationship that's given kilograms to pounds and kilograms to grams. So from pounds, we could go to kilograms using this one, couldn't we? And then this one could get us from kilograms to grams. So this is a situation, some people might be able to jump far enough over the stream if they can find the relationship between pounds and grams. But the rest of us are like, yeah, I don't know. I'm going to go with the stepping stone because I'd rather be sure than get my feet wet. So in the middle here, we're going to go to kilograms. So we're going to go from pounds to kilograms, and we know that relationship. 1 kilogram equals 2.2046 pounds. Okay, and then kilograms to grams, 1 kilogram equals 1,000 grams. I encourage you to learn how to show your work. Showing your work is great because if you're doing a problem and you can't get the right answer, you can bring me your work. I can look at it and see, oh, that's where you're going wrong. Otherwise, I have to teach you the whole problem and maybe you're just missing one little piece. It's also helpful for going back and learning from your mistakes. You're going to make mistakes. And you might as well learn from them. And so you can go back and learn from them. It's also good for reviewing for a test. You go back and look at the homework you've done. And you're like, I don't remember how to do that. Oh, here's my work. Oh, that's right. That's what I need to do. And so what I'm writing here is what I would like you to write down when you're showing your work. Okay, so we made a path, and we identified our conversion factors. How many fractions are going to be in this problem? 2. We have 2 arrows, so we're going to have 2 fractions. The numbers on the tops of the fractions are the one in the path. Getting the path is the hard part. And then it's just following some steps. So here's the Dora part. Pounds to kilograms to grams. That's in the path. That's what the map says. So then we need to go pounds to kilograms to grams. So we write that down. We've got pounds to kilograms to grams. Our path told us what to do. That's our unit path. And now we look and we see, well, I'm starting out over here with pounds. I need that to go away. I wish I could make dirty dishes go away this easily. We'll just divide by dirty dishes. We'll divide by pounds. Okay, and then the pounds cancel out. Now I've gotten rid of those. I need to get rid of kilograms. So I divide by kilograms and kilograms. Go away. Ta-da! Then we fill the numbers in. Dimensional analysis, it's unit analysis. The units tell us what to do. We put the units in first, and then we stick the numbers in. And we have to be careful when we stick our numbers in. Relationship between kilograms and pounds. Well, we wrote that down. 1 kilogram. I didn't leave enough room. That happens a lot. 2.2046 pounds. Then you ask yourself, does 1 kilogram equal 2.2 pounds? Yeah, okay. So I got that straight. Because the most common problem is people putting the 2.2 on top. They like to multiply by numbers. They don't like to divide by numbers. Sometimes you have to divide. Then over here, grams and kilograms. Well, that equation says it's 1,000 grams to 1 kilogram. So 1,000 grams to 1 kilogram. You can't switch the numbers. Now we use our calculator. The best approach is just like you're reading, start at the left and go to the right. Anything that's in the numerator, you multiply. Anything in the denominator, you divide. Now you don't have to multiply and divide by 1, but if you want to, it doesn't change anything. 4.5 times 1 divided by 2.2046 times 1,000 divided by 1. Press the equals button. Calculator says 2,041.186 6, 6, 1. And what unit do I have left? Grams. So there's what the calculator says. It's kind of messy. 2041.18661. Then we have to ask ourselves, how many significant figures should this have? So we look at our starting number. How many sig figs in 4.50? 3. This is a trailing 0, but there's a decimal point, so that counts. This has 3 sig figs. How many does this one have? 2.2046. 5. And how about this one? Well, that's tricky. That one's actually an exact one, because the relationship between grams and kilograms, within the metric system, the relationship is exact. Within the English system, the relationship is exact. That first one isn't exact because it's kilograms in the metric system to pounds in the English system. So our answer should have 3 significant figures. Okay, we need to be careful with this guy, though, because he's kind of a big number, and we're going to be rounding off the ones place, and so then we can get into trouble. So we should put this guy in scientific notation before we round off. 2.04118666 blah blah blah. This is just one more. Times 10 to the what? How many places did I move the decimal point? I moved it 3. And then you look at that number, 2041. Big number, small number? 2041 is a big number. Would you like $2,000? I would. I could buy myself a nice new laptop with that. I'm editing all my PowerPoint slides on this little tiny screen. Making me crazy. Okay, so put it in scientific notation. Now we're going to round it off to 3 sig figs. 1, 2, 3. This is the last one we're going to keep. We look at the next one that we're going to get rid of. It's a 1. So we just round it down. 2.04 times 10 to the third, and the unit is grams. And then it's always nice to put a box around it. Say, hey, here's my answer, this one right here. So we checked our sig figs. Now let's apply that bigger, smaller rule. Which unit is larger, pound or gram? You might have to think about that. A pound is bigger. So pound should have the smaller number and gram should have the bigger number. 4.5 is smaller than 2,000, so we've got the bigger, smaller thing going on. Because what happens is if you get your conversion factor numbers switched, you'll end up making the number, you'll change it in the wrong direction. If it's supposed to be getting smaller, you'll make it bigger. And so the bigger, smaller rule will often point out errors that you made in that calculation. Any questions? So, blah, blah, blah. I need to edit these, and I just have not had a chance. Okay, multi-step problems. That last one, the way we worked it, was an example of a multi-step problem. We couldn't just jump over the creek. We used a stepping stone in the middle. The steps that you plan out are based on what's available to you. What you know in your head, or what you're given on an exam, or what you can find in the book. Now, some of these multiple step problems, you're doing them at home as homework. And you could Google it and find this random conversion factor between these 2 steps and make it into a 1-step problem. I would encourage you not to do that, because you're not going to be able to do that on an exam. And when we get to stoichiometry, I think it's in chapter 8, we're going to have multi-step conversion things that there's no way to get around. You need to learn how to do this multi-step business. So shortcuts are going to hurt you in the end. There may be more than one correct way. You know, if you've got a stony brook and you're trying to get across, and you and 2 friends are going to go across, You all three may choose different stones to step on to get across, but you both end up in the same place. Some paths are easier, some paths are harder, but you do what you have available and what makes sense to you. So you can do these one conversion at a time. Like in that last one, we went pounds to kilograms to grams, and we strung it all together. You can just do the first one, pounds to kilograms, and find the answer, and then take kilograms and convert to grams. I don't encourage that, though, okay, because it's more work and it's easier to get lost. So I don't encourage that. I say learn to combine the steps into one equation. It'll be better in the long run. Let's do another example. The volume of a can of Diet Coke is 355 milliliters. What is the volume in centiliters? Okay. So we have to identify, what are we starting with? What are we given? We're given milliliters. We're given a volume in milliliters. So we've got 355. Oh dear. We've got, there we go, 355 milliliters. And what do we want to find? Centiliters. Do we know a relationship between milliliters and centiliters? Not off the top of our heads, we don't. This is a metric conversion involving prefixes, isn't it? So it's possible to do this in one step. I think it's more confusing, though. I've been doing these things for 31 years. I would still do this in two steps, just because it's straightforward. It involves less thinking. So here is an example of a metric conversion problem. When we look at our starting unit, it has a prefix. We look at our ending unit, it has a prefix. Two prefixes means we're going to take two steps. And the step in the middle is we're going to go to the unit without the prefix. So we're going to go from milliliters to liters without any prefix, and then we're going to go to centiliters. And this is where learning what those metric prefixes mean in terms of a mathematical number is really helpful, because we don't have to go look this up. We just ask ourselves, well, what does milli mean? Milli means 10 to the minus 3. So we can make these conversion factors. So this is one way to think about it. Let's do liter equals liter. Would you all agree with that? Mm-hmm. And I want to relate milliliters to liters. So I'm going to put milli over here. What does milli stand for? Milli stands for 10 to the minus 3. So I'm going to write what it stands for over here. Milli is like a nickname for 10 to the minus 3, or 1/1000th. And there, I have my conversion factor. Let's do this other one over here. Liters equals liters. I'm going to put centi on one side. What does centi mean? 10 to the minus 2. 1 centiliter equals 10 to the minus 2 liters. So you memorize the prefixes and what they mean, and you can make conversion factors for any metric units. Talk about efficiency. You learn one thing and you can apply it to all kinds of things. It's great. Okay. Oh, gosh. Now how to recover from that? Come back to me? I think I'm sunk. I think I have to do that all over again. Can you say learning curve? Okay, let's try it again. 355 milliliters. I'm going to convert to liters first, and then I'm going to convert to centiliters. Okay, in these conversion factors, I'm saying that liter equals liter. I'm going to write the prefix on one side, what it means on the other side. We needed a review anyway, didn't we? Liter equals liter. Centiliter. Centi means 10 to the minus 2. Okay, so now 355 milliliters times, how many arrows do I have? 2. I'm going to have 2 fractions then. Okay, the path says milliliters to liters to centiliters. So that's what I'm going to write in the numerator here. I've already got milliliters to liters to centiliters. So the path is telling us what to do. Now I want to get rid of milliliters. I do that by dividing. So I'm going to divide by milliliters, and those cross off. Those cancel out. Now I want to get rid of liters. I'm going to divide by liters. Those cancel out. You see how that works? Now I find the numbers and I put them in, because the units tell me where to put the numbers. We don't have to remember, do I multiply or do I divide? The units tell us everything. So we look at liters and milliliters, and we look at the equivalence statement we wrote, and 10 to the minus 3 was with the liter. Whoops. Was with the liter. Okay? Sorry, that ended up small. And over here, centiliter, 10 to the minus 2 was down here. So I'm teaching you a pattern with these metric prefixes. There are other ways to do it. Some of you may say, well, I'd rather say that 1 liter is 1,000 milliliters. That's fine, that works. But students get confused, and so I'm going to be consistent in how I approach it in my lectures. When we do it this way, we never have a prefix and a number together. Okay? The prefix is always by itself, and the number's on the other side. So now we have to do this on our calculator, and we have another small issue of what do we do with this 10 to the minus 3? 10 to the minus 3 is the same as 1 times 10 to the minus 3? That's scientific notation now, isn't it? So in your calculator, do 355 times 1 EE minus 3, or however your calculator details want it. Okay? If you want to, you can divide by 1, and then you can multiply by 1. You don't have to. And then divide by 1 EE minus 2. Press the equal sign. And so you should get 35.5. And the unit is centiliter. The other units all canceled out. What we have left, the letters we have left, we write down. Those are the units. When we're doing metric conversions, we always end up with the same number of sig figs that we started with. When we're doing metric conversions, we always end up with the same number of significant figures that we started with. And so this is just all those steps that I already did, because this is how I used to do it. And we're out of time, and so I'll see you on Wednesday.